What's up, future plant engineers? Welcome to today's explainer, built specifically for the heavy hitters at TVETMARA and KKTM Kemaman. If you're training to master plant operations, well, you're in the exact right place. Today, we're looking at the absolute most critical piece of machinery you'll ever deal with.
So, let me ask you a high-stakes question. Ever wonder how thousands of kilowatts travel from a power station to our plant without the whole system just melting down? Seriously, think about it. Why not just send 240 volts straight to the plant? Simple physics, guys. High current equals huge losses, specifically I²R losses. If we tried transmitting at low voltage, all that precious energy would literally just turn into wasted heat way before it even arrived at your facility.
To solve this massive problem, we generate electricity at, say, 11 to 25 kilovolts and then step it way up to 132 kilovolts or higher for efficient long-distance transmission. And the machine that makes this whole thing possible? The transformer. It's a static electrical device that acts as this powerful voltage translator. It steps alternating current voltage up or down without ever changing the frequency. Basically, it's what keeps the entire grid efficient.
All right, let's dive right into this. I want you to frame the essential oil-immersed transformer in your mind right now as the beating heart of the industrial plant. It is kind of like a high-pressure water pump. It adjusts the pressure, which in our world is the voltage, while the overall power flow remains exactly the same.
Moving on to Section 1, Electromagnetic Magic Explained.
So how exactly does this massive machine do all this heavy lifting? The magic inside this metal beast comes entirely down to Faraday's law of electromagnetic induction. Here's the three-step sequence you absolutely need to know. First, AC voltage is applied to the primary winding. Second, because it's alternating current, it's continuously changing direction. And third, this constant movement generates a changing magnetic field, or magnetic flux. This flux then induces the exact voltage we want right into the secondary winding. Now check out the core that actually holds these windings. Notice it's not just some solid, heavy block of iron. No, it's carefully built out of laminated silicon steel. Why do it this way? Because it kills off what we call eddy current losses by up to 90%. That changing magnetic flux passes right through this laminated core, which makes our plant operations ultra-efficient.
Okay, let's break it down in Section 2, Anatomy of a Transformer.
We're going to deconstruct this unit and look at the actual physical components you'll be inspecting out there on the job every single day. First up, the bushings. These guys act as vital porcelain insulators for the high and low voltage cables entering and leaving the transformer. They give the electrical current a safe path to pass right through the grounded tank, keeping you from dealing with a massive short circuit.
Next, look up top. That's the conservator tank. You see, when a plant is running at peak production, this transformer gets insanely hot, and the oil inside physically expands. The conservator tank gives that oil the breathing room it needs. And hey, if the pressure ever spikes dangerously high, a pressure relief valve, or PRV, will vent it out so the whole tank doesn't just rupture like a giant firecracker.
Now, connected to this system is the silica gel breather. And this right here is a totally critical visual diagnostic skill for any plant operator. When the transformer breathes in air from outside, this gel absorbs the moisture. Here's a pro tip to remember. If the gel is blue, you're good. It's dry and healthy. But if it turns pink, it is totally full of moisture and needs to be replaced immediately.
Right between the main tank and that conservator tank sits an absolute safety legend, the Buchholz relay. For any unit above 1 MVA, this mechanical relay is your very first line of defense. It literally catches gas bubbles produced by internal electrical faults. If things start getting out of hand, it connects straight to the circuit breaker's trip coil and shuts the entire system down way before a catastrophic failure can happen.
Let's shift gears to Section 3, Keeping Things Cool.
Since heavy industrial plants run so incredibly hot, and heat is the ultimate enemy of efficiency, transformers absolutely need a solid cooling routine to survive. We've got a few modes here. ONN, or Oil Natural Air Natural, is your standard mode, where oil and air just circulate naturally. It's super common for mid-sized units. Then we step it up to ONF, where fans actually kick in to force air over the radiators as the plant load starts rising. And for heavy-duty, industrial levels, we use OFF, Oil Forced Air Forced. That means deploying powerful pumps and giant fans for maximum cooling power.
Of course, we really can't talk about cooling without talking about the transformer oil itself. This stuff isn't just a basic coolant.
Whether you're using a standard mineral, hydrocarbon, or some expensive, non-inflammable synthetic liquid, this oil is actually acting as a primary electrical insulant and the main thermal transfer agent inside the tank.
All right, moving on to Section 4, losses and maintenance.
To keep our power from draining away, we rely on routine maintenance. Things like using a TTR meter to make sure the turns ratio is spot on, or Megger testing to verify that our insulation is sitting safely above 1,000 megaohms. But here's the thing. Even with absolutely perfect maintenance, you're constantly fighting a battle between two types of unavoidable energy losses that dictate the overall efficiency of your plant.
It is so crucial to understand the difference here. Iron loss, that is constant. It's made up of hysteresis and eddy currents, and it's dictated entirely by the physical design of that core we talked about earlier. Copper loss, on the flip side, is variable. It changes based on the heat generated by the load. Basically, the harder you run the plant, the higher your copper losses are going to be. Your true efficiency is just your output power divided by your input power, minus these two culprits.
Let's put this all together in Section 5, the ultimate power test.
Picture this scenario. It's peak production. Your transformer suddenly trips and alarm lights are flashing everywhere. Don't panic. Let's see if your diagnostic readiness is up to the challenge with a quick 3-question TVET sequence straight from the KKTM Kemaman module. Question 1. You're staring at the schematics. What is the fundamental working principle of a transformer? Think back to the start of this explainer.
Question 2. The pressure is definitely on. Which specific physical component holds and magnetically links both the primary and secondary windings?
And the final hurdle, Question 3. What is the exact purpose of a tap changer on the transformer? Lock in those answers.
All right, let's see how you did. For number 1, the working principle is Faraday's law of electromagnetic induction. For number 2, the component holding the windings is, for sure, the laminated iron core. And that tap changer for number 3, that's used to regulate the output voltage to keep everything stable. If you just got a perfect score, you're basically ready for the field.
We've covered the physics, the components, and the constant battle against heat and energy loss. So I'm going to leave you with this final thought. When you are finally out there on the floor, will you be the engineer who spots that pink silica gel or checks that Buchholz relay before it takes the entire plant offline? Master these fundamentals, stay grounded, and you'll be operating like a chief engineer in no time. Keep learning, guys, and I'll see you in the next explainer.